Okay, 1.2, day 2 of the notes. This is a little bit shorter, just 4 pages. So we talked how we were in the coordinate system. So we're in this Cartesian coordinate system, and I'm going to label my coordinate plane here with my x and my y-axes, as you're used to doing. And in this coordinate system, it's been divided into 4 quadrants. And as we start our initial ray here, and we rotating positively would be going counterclockwise, positive rotation. Our first quadrant would be quadrant 1, and it's going to be in that quadrant right there. And so they actually like to write Roman numerals in your textbook. So that's Roman numeral 1. And then quadrant 2, because remember, we're rotating positively, the second quadrant would be this upper left quadrant. And if I was writing that in Roman numerals, I would write it like that. And now we have quadrant 3, continuing our rotation. And this is the Roman numeral 3. And then the last quadrant, quadrant 4, as we're rotating positively, and Roman numeral for that is 1 before a 5, so it's 4, right like that. And, you know, in this Cartesian coordinate system, we're going to have some points with an x and a y coordinate, and those are going to help us define the terminal side. So that will help us decide where our triangle is, because remember, our initial side will always start from being in standard position on the x-axis. Okay, so distance formula. So I'm going to try this formula a couple times with 2 points to just review using the distance formula, but then you'll see on page 2 we'll have angles in standard position. So when they are, that means that one of the points will always be the origin. You'll see how that makes it a little easier. But so if we're going to use the distance formula at first, and we're going to use proper substitution and all that, we have r is equal to, now if we want this to be x1, this will be y1, this will be x2, and this will be y2. So now we are going to, and in this situation, it's always positive because always positive. We don't have to put the plus or minus because the square root was actually there already. So it's not us putting the square root, it's the formula has it. So it always wants the positive. But just substitute in. So x2 minus x1. So 3 minus negative 2, which actually will make it plus 2 squared, plus, now we go with the y2, 1 minus 7 squared, and then we put our square root back on. Okay, now to solve that, 5, that's going to get squared. Now I'm not putting parentheses around the 5 just because it is a positive number. Put my square root there. Plus, now let's see, 1 minus 7. That's actually negative 6, but I cannot write it like that because that would make it incorrect. I need to have the parentheses around the negative 6 to make sure that it becomes a positive 36. So continuing my work, 25 plus 36, square root of 61. I'm not going to use a decimal. I'm going to think about if that's prime or not. And it is a prime number, so I will leave it as root 61. Now you try the next problem. And I'll write out the work as well. Five squared Let's see, this is going to be a 3 squared. Still need my square root. Still need my square root. And I get 34, square root of 34. And I just got to check that 34 because I know a 2 goes into it and I'm just not, oh, well, but no pairs, so I'm done. Root 34. Okay, and then that is the distance formula. And what does the distance formula remind us of? It actually is a version of the Pythagorean theorem. And if you think about those coordinate points in here, for example, on the second example, how about I'll do that one, -3, so 2, 3, 1, 2, 3, 4. So here's this point at -3, comma, -4. And then the other point was at 2, 1, 2, -1. Here's my other point at 2, comma, -1. And we're trying to find the distance between these 2 points. And in fact, you can form a triangle either going up or going down. I guess I'll go up. Like here's this right triangle. And this is the delta x. Delta equals change. So the change in x, like how far away is a 2 from a -3? The delta x, the change in x was 5, wasn't it? That's how far a -3 is from a 2. And then on the vertical, we have our change in y. And what was our change in y? It was going from a -4 to a -1. So it was a change of 3. And so that's, basically we had 3 squared plus 5 squared equals c squared. But in this case, just the positive. So that's the distance formula, but it's really Pythagorean theorem. And that makes it much easier on the next page when we're working with things in the coordinate plane where one of the points will definitely be the origin. Because if I say that 6, 8 is a point on the terminal side, that is code for the other point is the other origin. Is origin. And so if that's the case, that's why I'm able to know that it's 0, 0. So if I have that, it makes this formula so much easier, because if I go back to my distance formula and this is my x2 and my y2, so 6 minus 0, because that's x1, squared plus y8 minus 0 squared. Notice how that, when you have something in the Cartesian system that is on the terminal side, it's basically just the Pythagorean theorem. And so my radius is 10. And radius, even in the Cartesian system, radius is always positive. Okay, next problem. So if I want to do this with, I could even skip writing the minus 0, but when you're squaring a 1 over root 2, make sure everything gets squared. One over 2 plus 1 over 2, because 1 squared is 1. Square root of 1. So this one right here has a radius equal to 1. Try this one on your own. I'm not going to bother writing the minus 0 because I know that that's going to drop away. It's a -2, so I do need those parentheses. Parentheses are helpful with the fraction. You really need them anyway. So now I'm going to square everything. A root 3 squared is 3. A 2 squared is 4 plus 1. Well, remember that negative gets squared, so it's going to be positive. 1 over 4. Square root of 1, it's 1. I can do this same process with x's. So let's see how this goes with this one. I know that the radius is root 29, and I want to find out what the y is, which I'm using x, an unknown. I'm using that. Okay, so think of your process. Okay, the square root of 4 squared plus x squared needs to equal root 29. Okay, to solve something like this, I'm going to square both sides in order to get rid of the square root. I'm going to do that before any subtraction. I cannot do anything with this side because of the plus sign that's embedded under the radical. So 4 squared plus x squared is equal to 29. 16 plus x squared is equal to 29. Subtract 16 from both sides. X squared is equal to 13. Square root on both sides, but because I'm the one doing it, x is equal to plus or minus root 13, a prime number. So now I'm going to write it as a point. Write the 2 points. 2 points. Okay, the first one has an x coordinate of 4, and although I was using x as my unknown, it really was meaning y. So I have x root 13, that was one of the points, or the other point will be 4 comma negative root 13. That's the other point. So we'd write both of our points, and we do that on the mini quiz. Okay, now I'm going to the next page just to look at some common measurements that go around a Cartesian coordinate system circle. This drawing is from page 22 of your textbook, and we're just going to go around this circle. Page 22 of your text has this in there. Remember, initial starts us off at the x-axis, so that's where 0 degrees is going to start us off. 90 degrees would be going straight up. So let's see, what do you think these measurements are here? These measurements are supposed to be the 45, this is the 30, and this is the 60. So you can kind of see how we're counting off as we go around, and these are going to be very important measurements. They're all going to be related to the 45, 45, 90, and the 30, 60, 90 triangle, as well as the special cases of 90, 180, 270, and 0. So these are going to be very important numbers that you're going to see a lot. So 30 degrees past 90 would be 120. This is going to be 135. This is going to be 150, 180, 210, 225. These are going to be very important numbers. All of these being at special locations in the unit circle. 300 degrees, 315, 330, and then you've gone all the way around the circle, so you're now at 360 degrees. And remember, I said we'd be mainly working with degrees in this course, especially at the beginning. So now that you have those in your mind, we can try to draw some angles. and we're going to draw some what are called coterminal angles, but this kind of gives us a basic framework of where angles might fall. And in these we will always draw the angle. See how that's capitalized? So start with your coordinate plane. Here's your initial ray. Now we'll draw 45 degrees. That's positive. So we are going to rotate positively, boom, 45 degrees. Now I want to get another angle that ends in the same place but has a different measurement. And that's what coterminal means. Co is together and terminal is ending. So how can I get another angle? And remember, always draw. So here's my drawing, starting on the initial ray, and I want it to end here, but I don't want it to be 45. I want to go all the way around and stop at 45. How far would someone have traveled? They would have traveled 360 degrees and 45 degrees for a total of 405 degrees. So that's how far they would have gone. And that would be a positive coterminal angle. And you could add another 360 and another 360. And every time you add a 360, you have a new coterminal positive angle. But what if I wanted to have my angle rotate negatively and end here? So in this case, I want it to go from my initial ray, I want it to go negatively to here. How far would someone have traveled to go that way? Well, you haven't gone all the way around. You've gone 45 degrees less than that. So let's write the work. 45 minus 360, because I'm going in the negative direction, and that gives me negative 315 degrees. So that's how far someone would have traveled if they were to start running here and run like this to get to the terminal side. That would take you 315 degrees, and that's a negative one. And every time I subtract a full rotation, I would get a new negative coterminal angle. You just have to give me one. All right, so my original angle is at 210. So let's draw where that is. We know it's past 90. We know it's past 180. It's in this quadrant right here, 210. Now, how can you get around the whole thing and then end it at that 210? So 360 plus 210, 570 degrees. Drawing it really shows you that you went 360 degrees, then you had to go another 210. That's arithmetic. Adding that 210. Now, okay, what if I'm here, but I want to go in the negative direction to there? How far is that, would I have to go? Remember, this other side was 210, so how far is the negative side? So 210 minus a full rotation, and that ends up with a negative 150 degrees. So negative, that's a coterminal angle. Okay, 450. To think about how we're going to draw 450, we know that we have to go all the way around to 360. We know that, but how much further do you have to go? Sometimes a little subtraction off to the side, and it kind of gives you an idea. Oh, okay, I've got to go 90 degrees. So like I'm going 360, and then I'm going to stop at 90, and that's what 450 degrees looks like as a rotation. So when I'm trying to get my positive angle, the easiest one to start at my initial ray and to end here, I would say the easiest one to say would be 90 degrees. But you would not be wrong if you wanted to go all the way around, and then end at 90 degrees too. If you wanted to say 8, how big would that be? Let's see. Is that 800? I got to double check this. 360 times 2 plus 90. Oh, B. Whoops, I plus 90 is, oh yeah, 810. Yeah, 810 degrees. You could say that. Those are both be the coterminal. They'd both be correct answers. And then if I want my negative, remember I'm starting here, I want to end here, and probably the easiest way to do that would be to go like that. And so that is negative 270. Now, if I did 450 minus 360, I have not gone enough because that's at 90. I still have a positive angle. So I have to take out another 360 and I get negative 270 degrees. So that was that first negative answer. Now this time I have a negative angle, but I want to get a positive angle for it. And negative 135 starting at my initial ray, going past 90, not quite to 180. I would expect negative 135 to be about here, but I need a positive rotation to that, so I am going to rotate like this, and so that would be negative 135 plus 360, and I get positive 225 degrees. Now let's do a negative rotation for that. Okay, negative rotation, but negative 135 is not enough. I got to go all the way around and then to negative 135. So negative 135 minus another 360, and I get 594. I get negative 495. Negative 420. 420. That's a big one. All right, well, I've got to go all the way around. It's 360. And let's see here. So 420 minus 360. I got to go 60 degrees more. So here we are. This is negative 420. Whoops, 420. Always draw your angles. So if I'm going to draw a positive angle going to there, just 60 degrees off here. So it's like this. Well, let's see here. That is going to be, that's negative 420. That would be 300 degrees. And a coterminal negative angle would be negative 60. So you just need to get one positive and one negative. 270, here's my initial. 270 actually is right here. So there's 270 degrees, but I need a positive and a negative. So why don't we go all the way around and then end right there. So that is 630 degrees. And if I start right here and I got to go down to here, that's negative 90 degrees. Okay, and that's the second day's notes. Try the mini quiz and the homework.